Okay, so hello everyone. In this video, we will cover deadlock handling methods and banker's algorithm. In this video, we will discuss 4 important methods used to handle deadlock situation in operating system: deadlock ignorance, deadlock prevention, deadlock avoidance, and deadlock detection and recovery. And at last, we will see banker's algorithm, which is very important algorithm. So let's start with deadlock ignorance, ostrich method. The first method is deadlock ignorance, also known as ostrich method. This approach simply ignores the deadlock when it occurs. You might think like this sounds funny. When a deadlock situation is occurring, we are simply ignoring it. But surprisingly, the majority of operating systems like Windows and Linux use this strategy widely. So what happens in deadlock ignorance? When deadlock occurs in the system, we simply ignore it. This is what nearly all users experience on their laptops. The problem manifests as system halting. The system gets hanged, and what do? We simply power off and restart the system. That is the essence of deadlock ignorance. Now, the fundamental reasoning behind this process is the deadlock occurs very rarely. Programmers think that deadlock occurs perhaps once in 5 years or once in 10 years. So why write full-fledged code to remove deadlock situation when it will affect performance? Consider Windows operating system. It already has extensive code for memory management, resource management, and many other functions. If we add additional code for handling and removing deadlocks, the system performance will be affected. We prioritize speed. So to maintain higher performance, programmers choose not to write code for deadlock removal. They believe that since deadlock occurs rarely, it's not worth writing complex code for such infrequent events. So the advantage is that the operating system focuses only on its major tasks without increasing functionality that could degrade performance. If we try to provide more and more functionality, the speed decreases. But nowadays, we are totally focused on speed rather than absolute correctness. 1 or 2 problems might occur, but these problems are very rare. So for rare occurrence, the simple method is to ignore the deadlock and restart the system. This method gets its name from the ostrich bird. When there is a sandstorm, so an ostrich puts its head into the sand. So essentially saying that there is no sandstorm, it's ignoring the problem. Similarly, in deadlock ignorance, whenever deadlock occurs, we simply ignore it. Deadlock situation don't occur daily. Since our system already have sufficient memory, CPU's capabilities and resources, if a rare deadlock occurs, we simply ignore it and restart. Now, what is deadlock prevention? The second method is deadlock prevention, based on principle of prevention is better than cure. Instead of finding solution when deadlock occurs, we try to find prevention solution before deadlock happens. The main approach is to work with the 4 necessary conditions for deadlock: mutual exclusion, no preemption, hold and wait, and circular wait. Since these 4 conditions are mandatory for deadlock to occur in the system, deadlock prevention try to remove all 4 conditions, or at least make one condition false. If any one condition become false, deadlock will be prevented. Now, removing mutual exclusion. Mutual exclusion means resource should be not shareable. They cannot be used simultaneously by multiple processes. To make this condition false, we would make all resources shareable, allowing multiple processes to use the resource at the same time. If this is possible, deadlock will be prevented. However, this approach has limitations. Not all resources can be made shareable. Resources like printers and tape drivers are inherently non-shareable, while resources like CPU and memory can be shared to some extent. Physical devices like printers cannot be made shareable. Since some resources cannot be shared, mutual exclusion cannot always be removed. Now, allowing preemption. There is second condition is no preemption. To prevent deadlock, we allow preemption. If processes P1 and P2 are in potential deadlock situation where P1 holds R1 and request R2, while P2 hold R2 and request R1, we can preempt P1. When P1 is preempted, it stops working and returns to the ready state, releasing resources R1. Now P2 can get R1 and complete its execution, preventing deadlock. This can be implemented using time quantum or time stamp method. A process runs for a specific time period, and after that it gets preempted. When preempted, resources are taken back and given to other processes, preventing deadlock situation. Now, eliminating hold and wait. To make this condition false, we ensure no process holds some resources while waiting for others. Before a process starts execution, we provide all the resources it demands. Although this is practically difficult because giving all the resources to one process would make other process wait infinitely, this theoretical method prevents hold and wait situations. Now, removing circular wait. For a deadlock to occur, there must be circular wait in single instances. So to prevent deadlock, we eliminate this condition. The method is to order all resources by giving them number. For example, if we have printer, scanner, CPU and register, we assign numbers: printer 1, scanner 2, CPU 3, register 4. The rule is that process can only request resources in increasing order. If process P1 requests resource R1 like printer, then it wants CPU, like it can request resource 3. However, if P1 already has resource 3 and then request resource 1, this request cannot be made because 1 is less than 3. So by enforcing this increasing order value, we prevent circular wait. If process P2 has resource 3 and wants to request resource 1, it cannot do so. Now deadlock avoidance. Deadlock avoidance involves giving resources to process while checking whether the result state is safe or unsafe. For every resource allocation, we verify whether deadlock can occur. If the allocation lead to an unsafe state, we don't allow it. This is implemented using Banker's algorithm. The Banker's algorithm is especially designed for deadlock avoidance by ensuring the system always remains in the safe state. Now, what is Banker's algorithm? The Banker's algorithm is also called the deadlock avoidance algorithm. In deadlock avoidance, we provide information to the operating system beforehand about which processes are coming, which resources they will request, how many resources they need, and for how long time. Based on this information, the system decides which process to execute and which is to make wait. Now, let's work like through an example. We have 5 processes: P1, P2, P3, P4 and P5, and 3 types of resources: A, B and C. The system has 10 instances of resource A, 5 instances of resource B and 7 instances of resource C. The algorithm uses several matrices, allocation matrices. So how many resources are currently allocated to each process? Maximum need matrix shows the maximum number of resources each process will need during its execution. Remaining need matrix calculated as maximum need minus allocation. So to find the available resources, we calculate total resources minus currently allocated resources. In our example, if the total allocation is 7 to 5 and total resources are 10, 5 and 7, then available resources are 3, 3, 2. The algorithm works by finding processes whose remaining needs can be satisfied with currently available resources. When we find such a process, we assume it completes execution and releases all its resources. Increasing the available amount, we will continue this process until either all processes complete, creating a safe sequence, or we find that some process cannot be satisfied, indicating potential deadlock. For instance, if process P2 need 1, 2, 2 resources and we have 3, 3, 2 available, we can satisfy P2. After P2 complete, it releases its all allocated resources, increasing our available count. We then check with other process can now be satisfied or not. If we can create a sequence where all processes complete, P2 first, then P4, then P5, P1, P3, we can first satisfy P2, then we can say how P4 is demanding. P4 is demanding that much of resources and we have that much of resources. Then P4 will execute and release its all resources. The resources allocated to P4, we will make it available. Then P5, then we will execute P1, then we will execute P3. So this is sequential manner. This is called safe sequence, indicating no deadlock will occur. So deadlock detection and recovery. The fourth method is deadlock detection and recovery. This approach first detects whether deadlock exists in our system using methods like resource allocation graph and then attempt to recover the system. Detection involves checking the current state of resource allocation and process request to determine if deadlock has occurred or not. If no deadlock is detected, no action is needed. If deadlock is found, recovery mechanisms are triggered. Recovery methods include process termination, kill one or more process involved in the deadlock, start by killing one process and check if deadlock still exists. If it is still present, kill additional process until the deadlock is resolved. This approach can harm system performance but effectively break the deadlock. Now, what is second one? Resource preemption. Preempt resources from processes involved in the deadlock. Take resources away from the certain processes and give them to other to break the circular dependency. This method is theoretically sound but practically complex to implement. But the choice of which process to terminate or which resources to preempt often depends on factors like process priority, with lower priority process being selected first. Now, what is the conclusion? Among these four methods, deadlock ignorance is the most widely implemented in real world systems despite other methods being theoretically available. This is because the performance benefit of ignoring the rare deadlock occurrence outweigh the cost of implementing complex prevention or recovery mechanism. The Banker's algorithm, while excellent for understanding deadlock avoidance concept, has practical limitations. It requires static advanced knowledge of resource needs, which rarely exist in our real system. So that's it for this video. We will meet in next video. Until then, bye bye.